So this is an introduction to humidity and why humidity is important. So if we're introducing the concept of humidity, we need to think about why is this concept relevant? Well, human comfort depends on humidity. If it's too hot or too humid, it's uncomfortable. If it's too dry, it's uncomfortable. If it's too dry, not enough humidity, wood can dry out. You can get things cracking, such as musical instruments, cigars we want to keep at a relatively high humidity. If the atmosphere is too humid, you can get mold growth. You can get bacteria growing inside, say, the wall of a building. So to quantitatively explore humidity, we need to first define some terms. So the atmosphere is a mixture of air and water vapor. So if we have the atmospheric pressure, we can write that as the sum of the partial pressure of air and the partial pressure of water vapor. So PA we'll call the partial pressure of air, and PV is the partial pressure of water vapor. So how do we quantify how much humidity is in the air? How much humidity is in the atmosphere? So the first method that can be done is using absolute humidity, also called specific humidity, or the humidity ratio. Many names for the same thing. This is done on a mass basis. We use this symbol omega, small omega, and it's the mass of the water vapor divided by Ma, the mass of air. Humidity ratio is the mass of water vapor divided by the mass of air. The second way of quantifying humidity is the relative humidity. We use the symbol phi. That's equal to PV divided by PG. PV, if you recall, it's the partial pressure of water vapor in the atmosphere. PG, this is the maximum possible partial pressure of water vapor. So this is the most we could have at a given temperature. We call this the saturation pressure. So at a given temperature, what's the saturation pressure? For a given temperature, we can look up this in the table. Pg is equal to the saturation pressure at the given temperature. Now, if we come back to the absolute humidity, here's the formula we had before. We know mass can be written in terms of the ideal gas law. So if we substitute that into the equation we had here, the partial pressure of water vapor, the partial pressure of air, the volumes cancel each other out, the temperatures cancel each other out, and we have a ratio of gas constants, which works out to 0.622. So we can write absolute humidity in terms of partial pressures. Now if we recall sum of these two partial pressures is the atmospheric pressure. So we can write the absolute humidity in terms of the partial pressure of water vapor and the atmospheric pressure. If we plot this on some diagrams, we'll plot the property of the water and the property of the air. For water, we have this trusty saturation curve. If we pick some arbitrary point, we'll call this point 1. The water is at a certain pressure, and we'll draw in the constant pressure line here. And this pressure is PV, the pressure of the water vapor. If we were to cool the air-water vapor mixture to point 2, we'll make sure they're both at the same temperature. Let's adjust this line here. Point 2 is on the saturation curve. So we're cooling it to the point of saturation. We call this point here the dew point. So if we cool at a constant pressure till we reach the saturation curve, this temperature at which we reach the saturation curve is called the dew point. And we can define the dew point temperature for a given partial pressure of water vapor. And cooling air follows a constant pressure line for PA, the partial pressure of air. Now at state 1, what is the saturation pressure? Which we called PG. You recall the saturation pressure is a function of the temperature. It's the saturation pressure at the given temperature for T1. So if we go along a constant temperature line here till we meet the saturation line, and we'll draw in a constant pressure line at that point of intersection. And this pressure along that constant pressure line is PG, the saturation pressure. More about the dew point. What is the dew point, and how do we reach it? When we cool down to the dew point at a fixed pressure, dew starts to form. No, not that kind of dew. The kind of dew you see on the leaves of plants. Outside, when it cools below the dew point, these droplets of condensation form. Fog also forms when the atmospheric temperature drops below the dew point. You have little droplets of condensation in the air. Here's an example of condensation forming on a window. This is when the temperature of the glass is below the dew point for the humidity and temperature of the room. So the glass is colder than the room, condensation forms on that glass.